Physics students, good afternoon. Mr. Fugit here. In this video today, we're going to be looking at one of the problems from your homework assignment number 3, which covers over kinematics in one direction, our study of how things move. Specifically, in this video, we're going to be looking at problem number 15, which involves something that we call vertical kinematics. Vertical kinematics, as you can probably guess, is still kinematics in one direction, but now, rather than that direction being horizontal, it's going to be vertical. Okay? Vertical kinematics is one of the last things we're going to cover in our unit on one-dimensional kinematics. So, if we haven't covered this material yet, I would encourage you, wait, okay? Maybe watch this video, wait till we've covered some of the material on vertical kinematics before you begin solving these last couple of problems. If not, some of the values that we use might be a little bit confusing for you. Okay? So, we're going to look at problem number 15, which covers over vertical kinematics. So in problem number 15, you're given a diagram, okay? And that diagram gives us a little bit of information. We're told that we're taking a ball and launching it upward with a velocity of 9 meters per second. Now, that velocity, since it's going to be our starting velocity, we're going to call that V0. That's going to be an important quality or an important variable going forward. Okay? Now, we're also told that the ball travels along some path upward and then eventually comes back down. Okay? And you'll notice in that diagram, there should be what looks like a marking for H max, meaning the maximum height. And that maximum height just occurs at the top, okay, of its trajectory. So let's read our problem statement, see what we're looking for here. Right off the bat, it says this. What is its maximum height? It being the ball. Its initial vertical speed is 9 meters per second, and the acceleration of gravity is 9.8 meters per second squared. For here, we're going to neglect air resistance. So what I'm going to do is I'm going to list out my variables, all relative to this vertical direction. So here, delta y, and notice again, we're dealing with vertical kinematics, not horizontal, so our displacement is going to be vertical, which is why we have a y here. My initial velocity, v0, in the y direction, and notice I'm making sure to represent that y direction with a subscript. My v1 in the y, my acceleration in the y, and my time. And remember, time is essentially a unit that's going to be applicable across x and y direction, so we don't need to represent it with a subscript. Now, delta y. Well, that's my displacement. And that's really what I'm looking for in this scenario. I'm looking for what is my maximum height from when I launch the ball to when it reaches the peak of its trajectory. So I don't really know my displacement, my delta y, but I am looking for it. So I'm going to put a star by that variable. My next variable that comes up is v0, my initial velocity. Well, we're told directly in our problem statement, our initial velocity is 9 meters per second. Now again, that's going to probably differ for you, but for me, that is the value I'm given. My v1 in the y, I'm not really told that explicitly. Okay, let's pause and come back to that. My acceleration in the y, well, I'm told is 9.8 meters per second squared. And it's the value for acceleration that I'm given. Okay? But, just as a quick reminder, that acceleration is causing our object to move downward, which according to our coordinate system, okay, downward in the vertical direction is what we call the negative y. And because that acceleration is pointed down, remember objects naturally want to fall toward the center of the earth, toward the ground, because it's downward, it's going to be a negative value. Okay? And here I don't know my time, so I'm going to put a question mark here. I don't know time. So it looks like what we need to try and figure out is what is my initial velocity? Or excuse me, what is my final velocity? When I reach my h max, my top of my trajectory, if you will. Okay? Well, one thing I want to show you really quickly. Okay? If we toss any ball up in the air, hopefully this won't break anything. Okay? This is essentially what we're doing here. We're tossing a ball and we're noticing how high it's going. Okay? Now, one thing I want to draw your attention to. As I toss this ball, I want you to think about what happens to this ball at the very peak of its trajectory. Notice it tosses up and then eventually comes back down. But at the very peak, once it reaches that top point, it's momentarily at rest. So I'm tossing it up, and just at a moment, it's going to stop before it comes back down. Maybe right there. I'll show you again, right there. Okay? You're seeing that ball essentially stop and change its direction to come back down because of that force of gravity pulling on it. So at the very top, when I reach my highest point, my velocity is really zero, right? Because I actually am not moving at that highest point. So what I'm going to model here, as I put my ball back, is that my final velocity in the y direction is in fact 0 meters per second, because that maximum height occurs when that ball stops moving, right? So I now have the variables that I need, not really concerned with time here. I'm looking for delta y. So let's look at our kinematics equation sheet. I go over to time, down to where it's blank and left. That tells me equation number 5 is what I'm going to be dealing with. So let's write that out. Equation number 5 looks like this. V1 squared is equal to V0 squared plus 2a delta y. Now here it's going to be very important that we take into account the direction that we're going in, as well as the units that we're dealing with here. So now I'm just going to plug in what I know. So my V1, my final velocity, remember, that's going to be 0. At the top of my trajectory, I momentarily come to rest. So this is 0, and any value 0 essentially squared is still going to be 0. So 0 squared is still going to give me a value of 0. We'll come to that later. V0, my initial velocity was 9 meters per second. I'll square that value eventually. Plus 2 times my acceleration, which was negative 9.8 meters per second squared, times my delta y. And delta y is what I'm looking for here. So what I need to do is I need to plug a couple of values in, try and simplify what I'm dealing with here. So I'm going to write my next step in red. 0 squared is still just going to be 0. That's going to be equal to 9 squared, which if I plug in, that'll be 81. My units here will be a little weird. I'm squaring meters per second, so I should get meters squared per second squared. Okay? Don't worry too much about the units if they're confusing you. I just want you to see where we're going. Okay? Then I'm going to add this to 2 times negative 9.8. That should give me negative 19.6 meters per second squared times my delta y. And now you'll notice it seems as though all of our values are really moved on this right side. So in order to get delta y by itself, I want to try to get rid of something over here. And the easiest thing I can start by getting rid of is this 81 meters squared per second squared. So let's do that. I'm going to subtract, I want to lose my work, 81 meters squared per second squared on both sides of my equation. Remember, that equal sign means that whatever I apply to one side, I have to apply to the other. If I subtract 81 from 81, that should go to 0. And what I'll be left with is an equation that looks like this. Negative 81 meters squared per second squared should be equal to, well, I have a negative 19.6 meters per second squared times my delta y, which is what I'm looking for. Now once I'm here, I know we've done a lot of work to get here. Now I can simply divide by 19.6 meters per second squared to get to my delta y. So let's do that. I'm going to divide by 19.6 meters per second squared on both sides of my equation. Make sure we are dividing by a negative. That's going to be very important here. So if I divide 19.6 by 19.6, that will get rid of that value on the right-hand side, and I'll be left with delta y is equal to negative 81 meters squared per second squared over negative 19.6. So I'm going to plug this in really quickly. Negative 81 divided by negative 19.6. Hopefully we'll notice those negatives, if I divide a negative by a negative, that's going to effectively give me a positive value. So I should be left with positive, in my calculator, 4.13. Now if I'm dealing with a displacement, in theory, my final unit should be in meters. But I don't want us to just assume we're dealing with meters. Let's check our units to make sure. So on top, I have meters per second squared, meters squared per second squared. On the bottom, I have meters per second squared. So my second squared, those units are going to cancel each other out. And I'll be left with meters squared over meters. So that's going to cancel out one of my units of meters and leave me with just one. So my unit here would be meters, which again tells me, confirmation, that my unit matches my variable. Delta y my maximum height should be 4.13 meters. Okay? Now, the reason that that's positive is because, come back to our picture. Remember, I'm tossing this ball upward, right? And we have defined that up in the vertical direction is positive y. So if I get a value that's negative, that's telling me it probably doesn't correspond with the scenario I'm dealing with. I'm not tossing this ball downward, I'm tossing it up, so my maximum height should be a positive value. Okay? I will remind you, as you go through, pay close attention to your direction, what we call positive and negative, as well as your units. And hopefully this gets you started on the right path to solving problems 15 and 16. Good luck.